This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome to Chapter 3 of our series, Mastering Lab Techniques Safely. In this episode, titled Mixing and Heating, Managing Reactions, we'll explore the essential principles of safely mixing chemicals and ensuring that reactions go off without a hitch. So, whether you're a budding scientist or just curious about lab safety, let's dive in. A quiet flask on a hot plate can be the most dangerous thing in your lab. In less than a minute, a calm swirl can turn into violent boiling, clouds of vapor, and shattered glass. Today, we're going to explore how tiny choices in stirring and heating decide which way it goes. A lot of lab training treats stirring rates and hot plate settings like background details. Set them, forget them, and focus on the real chemistry. But the data tell a different story. Most serious incidents don't start with exotic reagents. They start with unnoticed gradients in concentration and temperature quietly building inside ordinary glassware. A reaction that's perfectly safe on paper can turn unpredictable if one corner of the flask is far hotter or far more concentrated than the bulk solution. Just as a landscape can hide steep cliffs behind gentle hills, your flask can hide pockets of unreacted material next to overheated zones. In this episode, we'll treat mixing and heating as design variables, not afterthoughts, tools you can shape deliberately to control rates, steer selectivity, and keep energetic reactions firmly inside the safe window. In most labs, heat to reflux, stir overnight, is treated like a recipe line, not an engineering decision. But every degree and every swirl reshapes the energy landscape your molecules move through. Push the temperature a little higher, and the Arrhenius relationship quietly multiplies your rate. Fail to remove the extra heat, and an exotherm can start driving itself. Industry learned this the hard way with processes like Haber-Bosch, where built-in cooling is as essential as the catalyst. In this series, we'll borrow that mindset and scale it down to bench glassware, one controlled experiment at a time. A useful way to think about good mixing and heating is to separate what you see from what actually matters. You see a vortex, a stir bar rattling, a thermometer reading. What matters are three invisible variables you can control: how quickly fresh molecules meet each other, concentration field, how fast energy moves in and out, thermal field, and how long each part of the mixture experiences those conditions, residence time. Start with mixing. Magnetic stir bars mainly move the liquid in a toroidal loop. They're excellent for thin, low-viscosity systems where diffusion can finish the job. But once your solution thickens, forms precipitates, or separates into layers, that loop breaks down. An overhead or anchor stirrer can sweep the whole cross-section, pulling dense material off the bottom and breaking up temperature and concentration islands. Baffles or a slightly tilted flask can also disrupt smooth circular flow, creating more useful turbulence than simply turning the speed up. On heating, there are really two questions: how much power you feed the system, and how quickly that power, plus any exotherm, can leave. Hot plates report the surface temperature or an arbitrary level, not the actual heat flow. A modest setting with poor contact, dirty plate, warped flask, dry heating mantle, can produce hotter local zones than a higher setting with good contact and active cooling. This is why external baths, oil, silicone, metal beads, are so effective. They spread heat across the vessel wall and give you a big, uniform energy buffer. Cooling deserves the same intentional design. A cold finger condenser handles vapor, but it doesn't necessarily remove heat from the bulk. A properly chosen bath temperature, active stirring, and, when needed, an addition funnel or syringe pump to meter in reagents can keep the overall energy balance inside a narrow, predictable band. Nature offers a quiet analogy. A well-mixed lake warms and cools slowly, while a shallow, stratified pond flashes between extremes with every gust of wind. Think of three real lab snapshots. First, a nitration that behaves perfectly in a 10 milliliter vial but misbehaves in a 2-liter flask. The chemistry didn't change, the path heat and mass must travel did. In the vial, every joule and every molecule crosses the distance quickly. In the flask, the center becomes its own microreactor unless you deliberately design mixing that reaches it and surfaces that can export heat fast enough. Second, a crystallization that keeps oiling out. Often, the culprit isn't the solvent system, but a thermal history that cools the wall much faster than the bulk, letting droplets separate before the lattice can form. Swapping a still air bath for a gently stirred water bath can transform amorphous gum into crisp, filterable crystals simply by evening out that thermal path. Third, a flow setup where a coil in a thermostated bath quietly runs a reaction that failed in batch. Same reagents, but now every molecule sees nearly identical time, temperature, and concentration. AI tools that listen to your reaction via in situ IR, tiny temperature probes, or pressure traces will soon adjust mixing and energy input the way noise-canceling headphones counter background sound. Instead of guessing safe addition rates, you'll define boundaries and let algorithms search inside them for higher yield, cleaner profiles, and lower waste. In industry, that means fewer pilot failures. In teaching labs, it could mean students safely exploring bolder conditions. Treat each setup like mapping a new hiking trail. Note where heat enters, where it escapes, and how traffic flows through the flask. Over time, you'll start predicting where trouble or opportunity hides. Your challenge this week: pick one routine reaction and deliberately vary mixing or heating to chart how the outcome shifts. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!